Hello everyone. So we've heard some feedback regarding the labs. They're a little bit confusing. So in this video, we're going to go through and do a bit of a walkthrough for the labs that you can reference over and over again as a bit of not a walkthrough per se, but a bit of a clarifying video on the lab, and hopefully this can be a good resource for you as you're going through the lab materials. Now, this might be a little less useful than it would have been a few weeks ago. And depending on the feedback for this, we'll try implementing videos moving forward as well. Hopefully you'll feel confident approaching the lab and have a good way of locating yourself in the lab materials with this, although this should be an easier lab overall. So for this lab, I'll just go over what we touch on. It's this. I'm just pulling this from the textbook and then from using some things that I know as a TA. So we'll be going through finding the transfer function, as well as finding the characteristic equation, setting the natural frequency according to the rise time, some of the creation of the controller file, as well as the implementation of that controller file in your simulation, and then some thoughts on tuning as well. So as far as finding the transfer function goes, this should be pretty familiar to you for how to do this already. We've gone through a number of homework examples on the matter, but just as a refresher, working from theta tilde and working backwards, eventually we'll be able to create it so that theta tilde is on one side of our equation and theta tilde d is on the other side of our equation, and then we can just divide in order to find what the transfer function of theta tilde with respect to theta tilde d looks like. And the characteristic equation that we're going to get is strictly going to be the denominator of the closed loop transfer function that we found in the previous step. So now, as we get to the topic of setting our Kp and Kd, we give you a rise time to start out with, as well as a zeta value, and we already know what b theta is. So we can use our characteristic equation and define Kp and Kd. Now, if we recall that our characteristic equation is going to take the form of s squared plus 2 times zeta times omega n times s plus omega n squared, we can match coefficients and terms in order to solve for Kp and Kd. So Kp and Kd are just going to be in terms of those parameters that you will know. Now, to implement that controller and so that we can eventually use it in our simulation, it's going to be a very similar implementation as we've seen in the homework questions that deal with the design of PD controllers. So we'll want to set our rise time and zeta with, just as tuning preferences eventually, and for Kp and Kd, we can set those up just using the equations that we derived in the previous slide. And so we're going to want to include things like if you're working directly from the controller equilibrium file, you want to include things like the dirty derivatives, same previous values, and what have you. We'll want to implement our feedback linearization force, getting error in theta, propagating along theta dot. And now I could go on more about that, but I'll give a brief hint on the matter here. So this is the controller equilibrium file that you worked with previously, and you've been developing it, and so that's an option to start off from. And certainly you can go through the code and look at the homework problems, how they do PD controllers, and you'll find some similarities between this and the lab one. But there's also another option that you can use. which is if you look at the PID controller, which is in the public repo, you'll see that there's an implementation of a longitudinal PID controller, which contains prompts to help you get started on different variables that you should be using. And so if you want to work directly from the controller at Equilibrium file, that's totally fine. It's also okay to reference this file here for building out your controller. And it's just important to keep in mind that this template here is for a PID controller, and so you'll just have to keep that in mind as you're working through the lab. And so now to implement our controller in the Equilibrium in the simulation call of it, one of the main differences that we're going to see here is that we're going to need reference values as well for our error. And you've already seen some implementations in the homework simulations already of getting back the error, so you can reference those, and you should be feeling okay about implementing the simulation and the newly designed controller. And as far as steps for the hardware, when I was looking through the textbook, it's very explicit on steps that you should be taking for tuning your gains on the hardware. Just as a note, which the textbook also does say, is that we're sort of expecting there to be a little bit of steady state error, but the important thing here, especially for your tuning, is going to be dealing with significant oscillations, and it walks through the steps on setting up your gains according to that as your priority in the textbook. I think that's everything to cover as far as the lab goes. Hopefully this is a useful guide. If you notice any issues or what have you, put a note in the Teams chat, and we'll and I'll go back and I'll review.